Okay, so I think we can continue. So we looked at the electric potential of a point charge last time. So today we're going to look at the potential of many point charges. We'll just use the superposition principle to do that. So this is chapter 28. This is 28.7, potential of many point charges. Okay, so I'll just remind you of what we had. So we saw last time the potential of a point charge, let's say Q, at some point R. So we can say that the potential V at R is equal to K Q over R. That's the basic formula. Okay. And so if you have multiple point charges, we can find the potential at a point, say P, due to these charges. And so we can say that, let's say we have several charges. Let's call this Q1, Q2, Q3. We can have Q4 all the way to say Qn. So the potential at some point here will be at this distance. Let's call it R1. This distance is R2. This will be R3. We can say that there's a distance here. Let's say Rn. And this one is R4. So this is Rn. So the potential at P is the sum of the potential due to each of these charges. So it's going to be the potential. So this point is P. Okay. The potential at P due to 1 plus potential at P due to 2 plus potential at P due to charge N. So we can say that the potential at P is just the sum of all the potentials, like that. So this gives us a potential at some point in space due to a collection of point charges. So next, we can find the potential due to a continuous charge distribution. And we shall do the same thing we did for the continuous distribution of charge the electric field due to a continuous distribution of charges. So we can start with, say, a ring. So I'll do the example of the ring. Or actually, before we do that, let me just give you the formula that we can use for this. So we can start with the formula for different distributions. Okay, so let's say we have a line. Then we can say that if we have a uniform charge density on the line, lambda is equal to total charge Q over L, where L is the length of the line. So we can take an element on this charge, on this line dq, okay, and we can say that the potential V is equal to the integral of K Q over R, where dq is equal to lambda dx. In this case, we can take a line of length dx. Okay, so this will allow us to find a potential for a line at some point in space, and then for a surface, we can do the same thing. So we have a surface of uniform charge density eta. We shall say eta is equal to Q over A for the surface. And so if we take an arbitrary surface, then we take a certain element dA on that surface, it will have a charge dq. Therefore, we can say that eta is equal to dq dA, and so dq is equal to eta dA on that surface. So we can say the potential V is equal to the integral over the surface of K dq over R, which can be written as the integral K dq, which is eta dA divided by R. So we can use this as an example. We can use this to find the potential due to the ring. Let's start with the line. I'll do an example of the line first. So we'll start off with the potential of a line of length L at let's see, at some point. So we want a potential of a line of length L at some point P in space. We can say the line has a uniform charge density lambda, not eta, sorry, lambda, uniform charge density lambda, and the total charge is Q. So charge density lambda, which is equal to Q over L. Okay, so we put a line, total length is L, and then we say at this point P in space, if we take an element, the Q of length, the X, and the distance from here to here is X. This is X, so the whole line has length L, of course. Okay, so here is what we have. So this distance, let's say, is Y, and this is X. So this whole thing is the square root of Y squared plus X squared. Okay, so we can use our formula that V is equal to the integral from 0 to L of K dq over R, or over some distance R, which is the square root of Y squared plus X squared. And then we'll continue with that. We shall say that the potential V is equal to K. We take that out, 0 to L. And dq, we can replace dq by lambda dx divided by square root of Y squared plus X squared. And we can say that dq is equal to lambda dx due to the charge being uniform. So it just remains to integrate this, and the integral is in the tables. So there's an integral in the table. So we'll say that using integral table, so we're using an integral table. So we'll say that the integral of dx over square root of Y squared plus X squared is equal to, in this case, natural log. It's going to be natural log of X plus square root of Y squared plus X squared. So that's the integral according to the table, 0 to L. Let me rewrite this. I'll just write it here. Sorry, I ran out of space, so give me a second. So the integral from 0 to L dx over square root of Y squared plus X squared is equal to natural log of X plus square root of Y squared plus X squared, 0 to L. So using that, we can say the potential V is equal to K lambda times the natural log of X plus square root of Y squared plus X squared, 0 to L. And so plugging those in, we shall say K lambda natural log of L plus square root of Y squared plus L squared minus, so let's put this here, natural log of 0 plus square root of Y squared, which plus 0, of course. So we shall say V is equal to K lambda natural log of L plus square root of Y squared plus L squared minus Y, natural log of Y, sorry, natural log of Y. And we can say that lambda is equal to Q over L, and K is equal to 1 over 4 pi epsilon naught. Therefore, the potential for the line at that point P is equal to Q over L times 4 pi epsilon naught. The L is just the length that I've used, so let me write it the way I've been writing it so it doesn't lead to confusion. So this is L, and this will just be in parentheses natural log of L plus square root of Y squared plus L squared minus natural log of Y. Okay, I think that should do it. Note that in this case Y is not a variable. Okay, so let's make a note. So Y is not a variable. So Y could be any letter, like I could have used a constant like A or B or any of those things. So Y is not a variable. Any questions at this point? Okay, let's try another one. This time we shall do the ring. So consider a ring of radius R lying on the xy plane if the ring has a uniform charge density, let's say lambda, uniform charge density lambda equal to Q over L. What is the potential of the ring at point P shown below? So this exercise that I'm giving you is like same as the potential of the ring in your textbook. It's just an example in your textbook. Your textbook lays it on the side. I can do it in a different way. So we'll see. We'll just set it up in a similar way. So this is our ring. And we are saying that we want to find the potential at some point. This is along the y. So let's say potential at some point P. So we take a certain segment of the ring like that. That segment has charge the Q and length the S and the radius R, which is uppercase R. And so this distance from here to here is going to be the square root of, and let's say that this, let's call this a certain letter A instead of Y, so that we know it's not a variable. So we'll say this is A squared plus R squared. So we are finding the potential at a point P. So the potential at P is equal to the integral over the entire ring. Let's say this will be the integral over the entire ring of K dq over R. And so dq is equal to lambda ds, where ds is equal to R d theta. Okay, because that length ds is the small length of an arc of that circle there. Let me see if I can illustrate this better for you. So hold on a second. I'll show you in a minute. So let's say this is the radius R. So I'm taking here a length, and this small angle is the theta. So this is R also, of course, but this small angle here is d theta. Okay, so the length of the arc ds is equal to R d theta, so dq can be written as lambda R d theta. And so putting all that in, the potential at P, this time I'm just going to integrate from 0 to 2 pi, because I want to go over the entire circle, 0 to 2 pi of K lambda R theta divided by the square root of A squared plus R squared. And notice that we are integrating over theta, so none of those things under the integral sign is a variable, so we can take them out. So we take K lambda R over the square root of A squared plus R squared, and then we integrate from 0 to 2 pi d theta. So see if you can finish this integral. Take it from here and do the integral and write the formula. So I'll say that, show that Vp is equal to, so we're going to show that the potential at some point P is equal to Q over 4 pi epsilon naught square root of A squared plus R squared. And so from here you should be able to show that. Okay, let's take a look here. So the solution is this. So we say the potential at P is equal to K lambda R over the square root of A squared plus R squared, integral from 0 to 2 pi d theta, which we can write as K lambda R square root of A squared plus R squared, and your integral is theta from 0 to 2 pi. So the potential at P can be written as K lambda 2 pi R divided by square root of A squared plus R squared. The 0 goes away, of course, where we can replace K by 1 over 4 pi epsilon naught, and lambda is equal to Q over 2 pi R, because the length of that circle, the circumference there, which is the length, is just 2 pi R. So we can say that the potential at P is equal to K, which is 1 over 4 pi epsilon naught, lambda which is equal to Q over 2 pi R times the 2 pi R on top divided by the square root of A squared plus R squared. Okay, so this goes away and you are left with Q over 4 pi epsilon naught square root of A squared plus R squared. Try example, this is 28.13. This is in the third edition of the book.